Assalamualaikum warahmatullahi wabarakatuh. In this video, our group will present about application of mechanics in real life, and for our topic is Newton's law. Before we start our presentation, let me first introduce our group member. Starting from the left, his name is Adam Muhammad bin Yusman, followed by Muhammad Iqbal Hakimi bin Khairul Anwar, and me is Muhammad Shazrul bin Sharudin, Muhammad Husaini bin Muhammad Husin, Muhammad Faizi Aziz bin Ghazali. So let's move on to introduction to Newton's law. Newton's law of motion are three fundamental principles that explain how objects move and interact with forces. They were introduced by Sir Isaac Newton in 1687 and form the foundation of classical mechanics.
Now let me introduce Newton's law of motion. Newton's first law, law of inertia. Newton's first law states that an object at rest will remain at rest, and an object in motion will continue moving at a constant speed in a straight line, unless acted on by an unbalanced force. For example, think of a soccer ball. It won't move until you kick it, and once it's moving, it will keep going forever if friction and gravity didn't stop it. Newton's second law, F equals to m multiplied by A. Newton's second law is summed up by the equation F equals to m times A. Force equals to mass times acceleration. F is force measured in newtons, m is mass measured in kilograms, and A is acceleration measured in meters per second squared. For example, pushing a shopping cart lightly makes it accelerate slowly, but pushing harder, more force, makes it speed up faster, especially if it's not loaded too heavily. It is less mass. To sum up, first law, objects keep doing what they are doing unless a force interferes. For second law, force needed on mass and how fast you want it to accelerate.
Let's move on to the next topic, application of Newton's law, first law inertia. For the first situation, shuttlecock at rest doesn't move until hit. Before the shuttle is served, it just stays in the air or on the racket. That's inertia like. The shuttle resists motion until you apply force by hitting it. This shows an object at rest stay at rest until act on by force. For the second situation, shuttlecock continues flying after being hit. When you hit the shuttle, it doesn't just stop mid-air, it keeps moving. This is inertia in motion, and only slow down because of air resistance and gravity. An object in motion stays in motion unless act on by external force. For the third situation, racket movement after hitting the shuttle. When a player hits the shuttle, their racket doesn't stop immediately. It continues to swing a bit due to its inertia. That's why follow-through is common in badminton techniques. For the fourth situation, heavier racket has more inertia. A heavier racket has more resistance to change in motion. It takes more force to start or stop it. That's why lighter rackets are easier to maneuver quickly, especially for fast release. More mass equal to more inertia.
Next, we move on to the application of Newton law, which is the second law of Newton law. So, in a badminton match, a player are using different rackets to hit the same shuttlecock. Racket A has a mass of 78 grams and applies a force to the shuttlecock, producing a certain acceleration. Other than that, racket B is heavier, with a mass of 93 grams. Let's assume both rackets hit the same shuttlecock and we want the shuttlecock to experience the same acceleration when hit by racket B as it did with racket A. The shuttle traveled 1.65 meter from the initial position by 3 seconds. How much force must be applied? how much force must be applied by racket B to achieve the same acceleration.
Alright, let's move on to the calculation. List all the information from the questions. First, mass of racket A is equal to 78 gram, which is 0.078 kilogram. Next, mass of racket B is equal to 93 gram, which is 0.093 kilogram. The shuttlecock travels in 1.65 meter in 0.8 seconds. We want both rackets to cause the same acceleration on the shuttlecock.
Next, we will find the acceleration using shuttle motion. Use kinematic formula S equal to ut plus 1 over 2 at squared. We assume that initial velocity u is equal to 0. Then, after we calculate, we get A is equal to 5.15625 meter over s squared. Next, we use Newton's second law for racket A to find the force that must be applied to achieve the acceleration in 0.8 seconds. We use F equal to ma, where F is equal to force, m is equal to the mass of the racket, and A is the acceleration. Then we will get the force for racket A is approximately 0.402 Newton. On top of that, we use the same formula to find the force that must be applied to racket B to achieve the same acceleration in 0.8 seconds. Then we get approximately 0.480 Newton of force to achieve the same acceleration.
From my previous groupmate Muhammad Usaini calculation explanation, we can see and conclude that in Newton's first law, it explains why a shuttlecock remains at rest until a force is applied to it by the racket. Meanwhile, Newton's second law explains how the force applied by the racket affects the acceleration of the shuttlecock. Last but not least, Newton's law explains every motion in badminton, from the serve to the smash to how your body moves on court. By understanding these laws, players can improve power, speed, and control in their gameplay.